Okay, let's get started. Today we talk about the ceramics and also fatigue damage and finish the fatigue damage for the composite laminate. And then we talk about the ceramics. We know fatigue, right? So we know fatigue. And fatigue means that you apply the load cyclically, periodically, and even though the load level, the magnitude of load can be relatively small, but if you apply this load continuously, and finally as the time goes, so this material will fail. So we know the fatigue. Cyclic loading of composite panels, and then we now talk about composite panels. Our panels here are referring to these samples of work pieces, and produces essentially the same type of damage as a monotonic loading. And you should know that, as I said, even though cyclic loading, the magnitude of the load is low, but as the time goes, the cyclic loading can cause bigger problem. And the research shows that in industry, most of the failures, the components failures, are because of this is the cyclic loading. Right? So for these composites, and we will have the fiber rupture, reinforcing fibers. I'm talking about reinforcing fibers, fiber ruptures, fiber breaks. Matrix, the cracking matrix is the major the material, and the fiber and matrix debonding. For some reason, the fibers is supposed to be lying on in this matrix, but as the time goes and this cyclic loading, the fiber and matrix debond each other. And then delamination. So all these things, and they are commonly seen the failure mechanisms, and all these can be occurring in response to the fatigue loading. And fatigue damage reduces the strength and modulus of a composite laminate, and this we call laminate. Okay, laminate. These composites, a lot of laminates. One laminate can have multiple layers, or what we also call pliers, and eventually lead to the total failure. So suppose this is the composite panel. We call panel this is samples here. Let's just use a sample. We call this a panel, and so here is a force. We can see if we apply this is a remote force. So this force is not monotonic force. However, this guy is fluctuating. This guy is cyclic. For example, if this guy is applied in the shape of the sine function. So the first figure illustrates how this is normalized residual strength and decreases as the number of cycles increases. So this is normalized. Okay, so this is normalized. So here this normalized means that the actual number of cycles divided by the number of cycles for this is the panel to fill. So this is capital N. So this is normalized. And here is normalized residual strength. And residual strength at the very beginning, we say this residual stress is very, very high. Okay, so we use that one to divide all this is instantaneous this is strength as the time goes. And we will know that at the very beginning, so normalized residual strength equals 1. As the time goes, as the number of cycles goes, so this goes down quickly, and then from this point 2 to point 8, and we can have a relatively the flat. This is the plateau, the flat area, flat line, and then after point 8. So this is the strength goes down much quickly. So similarly, And for this is the normalized residual modulus. Modulus is a strength. Modulus. What is a modulus? Young's modulus. This kind of modulus. We can also see normalized cycle and also this normalized residual strength. And also, so you can see if we look at these two figures, we can see that so these two figures they have a very similar in the shape. Okay, so it goes down quickly, and then at one point to the point 8. So this is it is a flattening, is a flat the segment, and then it goes down until it fully the fill. So you can see on both strength and modulus decrease rapidly without relatively few cycles, after several few cycles, but remain approximately. So these are two plateaus. This is one plateau. So this is another plateau in the modulus. Remain constant up to around 80% of the fatigue life. Near the end of the fatigue life, strength and modulus decrease further. So this is how these composite panels, composite samples respond. And if we apply this is a cyclic loading or this fatigue and this condition of fatigue. Then we talk about the ceramics. Okay, so we have talked about the composites, polymer composites. Then we talk about the ceramics and talk about ceramics and ceramic composites. So we know ceramics, right, guys? So ceramics are used commonly in our daily life. For example, the dishes, right? The dishes, the bowls, and all this is the containers we use in oven. In this is also in this microwave, and they are made of ceramics. For the metal, we supposedly we should not use this is utensils made of this metal or metal alloys in the oven or in the microwave. It's barely in the microwave, right? We know that if we put a metal piece, then we microwave it. What will happen, guys? Huh?
Like an explosion or
Yeah, and maybe we'll see something bad. Okay, that's the reason there is warning sign saying don't put any metallic piece in the microwave. Right? You don't want to see bad things. Don't do that. Okay? Why? Physically, why? Because we have a microwave. This is the metal is electrical conductive, and so they can have short circuit. It's a very bad thing. So, but ceramic is okay, and you can simply put the ceramic in the oven or in the microwave oven, and either way will be okay. Why? Because these kind of materials they usually they can survive very high temperature. So as a result, the engines for the heat engines, for example, the Boeing this is aircrafts, the engines, they are made of these ceramics. What? So some engines they are still made of titanium alloy, but some if the temperature is very high, they need to use the ceramics. So this is heat engines can have a service life at this high temperature and for about 3,000 hours. So this is very good, a very good one, a very good material candidate. And for working conditions, if the working conditions is greater than 2000 degrees C, and only ceramics, all the metals, the no metals cannot fulfill. This is the requirement. So only ceramics. So ceramic materials, they include oxides, metal oxides, and that is compound of some metallic element, with this is oxygen. The carbide, carbide is something, some metallic compound reacts with this is the carbon, and we have carbides and sulfides, also metallic materials. Metallic material reacts with this is sulfur, and or this intermediate compounds, so which are either joined by covalent or ionic bonds. And covalent and ionic bonds, and they are very tough. and this bond is very strong, very strong. Right? So on the oxides, carbides, and sulfides, and the intermediate compounds usually is crystalline, but they are not close packed plane, don't have no close packed plane, and no dislocation. So if this can have dislocation, that means this guy can survive the plastic deformation. So as a result, so this is intermediate compounds, and even though they exhibit this crystalline, this is a structure, but they still is brittle. Right? So the brittle, that means the ceramics they are brittle. So most traditional ceramics are monolithic. Monolithic here means the single phase, and have very low fracture toughness. You can see, and even though this guy can withstand a very high temperature, and however, and when we talk about this is a loading, mechanical loading, especially so this is impact, so these kind of things, they have very low fracture toughness. What does that mean? It means that so this guy are very brittle. Okay, it's very brittle. If we have impact, or we have this is a sudden, this is a loading, and so this they can just fracture very easily. So because they do not yield, right? Because they are brittle, they do not yield. Yield means that so this elastic limit is reached, and now the material is going to behave plastically. But now, no. So this guy does not yield. These ceramics do not yield. So that means no yielding, only the elastic, and then they can have very brittle, and a propagating crack need only overcome, and so the surface energy of the material. Okay, and we know that in order for this sample, in order to have cracks, as we need to overcome several things. The most important thing is the surface energy of material, right? Because you are going to produce new surface. Any cracks, they have two surfaces. If you want to produce new surfaces, you must consume the energy. They call surface energy. Also, if this material is volatile material, and you also need to overcome the plastic deformation. So as a result, because the ceramics, they do not have plastic deformation, and you only need to overcome the surface energy of this material, and then you can have cracks. So that's the reason this guy is much easier to fracture. So the new generation, however, so because our human being, we always want to do something innovative to satisfy our current needs. And the new generation of ceramics, however, includes multi-phase materials and ceramic composites. That means we have ceramic parent material, and we call ceramic this matrix. And then within this ceramic matrix, we add some these multi-phase materials, and to vastly improve the toughness. Under certain conditions, two brittle solids can be combined to produce a material that is significantly tougher than either parent the material. Right? So, and how people what kind of the ways people have used to enhance the toughness of ceramics, and there are several. I guess, as I said, and even though this is kind of conceptual knowledge, but if in the final exam, if I just ask you, what are the toughening ceramic toughening mechanisms, and you need to compare, you know how to compare and to get the results. Okay? You understand this? I will not give you anything that I have never talked about. I only test your understanding of the problems that I have taught. You understand this? So whenever I say, please use your own words to tell me what are the commonly used ceramic enhancing mechanisms here. So the ceramic toughening mechanisms, and we have two categories. One is called process zone formation. This is a process zone formation. Another is called the bridging. So we have two big categories. So for the first category, we can just characterize them further. So first one is microcrack toughening, and second one is transformation toughening, as the name suggests. And transformation means that, and by some means, we just accomplish the phase transformation just around this crack tip transformation. The third one, the ductile phase toughening. So as the name suggests, and we put something ductile and some particles and in front of the crack tip, all this around the crack tip, and to accomplish the enhanced toughening. So this is the first category. The second category is more physically intuitive, and we use a fiber whisker to bridge and to toughen. And so this is the ceramic. The toughness, you can see the toughness has a unit of megapascal square root meter. Can somebody tell me and what the parameter we have talked about and have this kind of the unit? Megapascal square root m. Bobby.
Stress intensity factor.
Yeah, right. Stress intensity factor. So for the brittle material, the stress intensity factor is very, very important. So usually, the brittle material can be categorized. The fractures in the brittle material can be categorized using, and this is a stress intensity factor. So the above toughening mechanisms for ceramics are divided into two categories. I told you guys, process zone formation and bridging, and both mechanisms involve energy dissipation as a crack tip. So, from the perspective of energy, that means we want to consume more energy before the crack forms, right? So how can you consume more energy before finally you can your specimen can fracture? So this, if you can do this, that means you can toughen your sample. So the third mechanism is the crack deflection, and elevates the toughness by increasing the area of the fracture surface, as shown below here. Right? So if you can just deflect the crack, the growth is a crack parts, and you can improve the area of the fracture surface. As a result, and you can just toughen your material. Right? Three categories. So this is third category. So this is a process zone, and second one is bridging. And bridging, as I said, bridging is physically intuitive. So this is a crack, and we just do something. We can have some fibers and all these whiskers, and to connect the two surfaces of this crack, and make sure that when you want to open this crack further, you need to break. This is the bridging. Either fibers or whiskers first. And if you break these fibers or whiskers first, and you are going to consume more energy, as a result, you are toughening this ceramic material. Right? Questions so far? So, schematically, so the brittle material usually TR is a constant, and however, if we use some means, some mechanisms, and to toughen this ceramics material, and we can have this kind of a toughened ceramic, which exhibits the similar curve for the ductile material. Do you still remember, guys? Do you still remember the GR curve? Right. So we know that for the GR curve, the brittle material, the GR curve is usually the flat one. But for the ductile material, it is increasing, and this is this curve keep increasing. But if we do something to toughen the ceramics, we can make sure So this GR curve and they exhibit the similar curve as the dark material instead of this flat one. Right? So this is the toughening. And then we talk about each of these one very briefly. And for process zone formation and for process zones formation, the critical strain energy rate means that if the strain energy rate you calculated is greater than this one, the crack propagates. The critical energy strain release rate for propagation equals the work required to propagate the crack from A and to A plus dA divided by this dA. So here we assume the thickness is a unit thickness. And so here is the GR. So I just tell you this is the GR, right? The GR is surface energy, right? If, guys, you can see, if and so this material has not been toughened, that means the original material, ceramic material, and we do not have the second term. We only have this one. Okay? The 2 divided by multiplied by surface energy. And why we have the factor 2 here? Because we have 2 surfaces. Whenever you have a crack, you have 2 surfaces. One is up, one is down, right? Okay. So here, this one is based upon, so this is the toughening mechanism. You can see sigma ij, d epsilon ij. So here, so this integration is called strain energy density. And strain energy density, and then we do the integration again, and then y with respect to y. So this one will be energy, right? So this is gr. This is energy and this energy. And also we assume the thickness of the sample has the unit the thickness. So the H is a half width of the process zone. So we know that for linear elastic material, the strain energy density can be written as 1/2 sigma ij epsilon sigma ij. Sigma ij multiplied by d epsilon ij. I appears twice, right? I is a dummy, and J appears twice also, and J is a dummy. Right, guys? So I told you guys, dummy means summation. That means, so you need to do the summation. I, for 3D, I goes from 1, 2, 3, and J also goes from 1, 2, 3. So you need to select 1, I for 1, J for 1, and so on and so forth, until you have all these things to sum them together to get the total strain energy density. And for simplicity, we use this is Einstein notation. And as I said, I appears twice in this term. That means I is a dummy, and J appears twice, and within this term also J is a dummy. And dummy means summation. So this is for the critical for the process zone formation. And for bridging, this is for bridging. And we also have 2 terms. So this term is the term that if we do not have any toughening mechanism, we only have this one. However, this time we have some whiskers or these fibers that connect. This is upper face and lower face of the crack, and then we will have sigma yy, and sigma yy is in y direction, and d delta y is delta y. DC is from you want to the crack. This is crack. So volume F is the volume fraction of these bridging fibers, and what is the volume fraction of these bridging fibers or whiskers? So this is similar to the Dugdale and the Brand strip yield model. So I just want you guys to know we have these 2 models. I will not ask you guys to do any calculations. And then we go through all these is the mechanisms. The first one is a micro crack toughening. So there are some things, even though the formation, okay, we do not want cracks in our the sample. So even though, however, even though the formation of cracks in material is generally considered deleterious, that is detrimental, and is not desired. However, micro cracking can sometimes lead to improved toughness. Why? And this is counterintuitive. So why? Consider a material sample of volume V that forms N microcracks when subject to a particular stress. Right? If these cracks are penny-shaped with the average radius A, penny-shaped, the total work required to form these microcracks equals the surface energy times the total crack area. So this is WC equals this one. So the generation of stable microcracks. So the formation of microcracks releases the strain energy from the sample, which results in an increase in the compliance. So if this change in compliance is gradual, right? As existing microcracks grow and new cracks form, a nonlinear strain curve results. So the change in strain energy density due to the micro formation is given by using this one. So this N, capital N, is the number of these microcracks. So you need to have this delta W first. You need to have this delta W first. So this is for microcrack, the toughening here. And second one is transformation toughening. And as the name suggests, and we need to have some phase transformation in front of the crack. You can see? So some ceramics materials experience a stress-induced martensitic transformation. And you guys know martensitic, right? Martensitic. Hey George, what is martensitic? Material, recall, material science. Martensite, perlite, barite, Michael.
I don't remember that.
Martensite. Martensite is a unique microstructure or nanostructure, and it occurs when the cooling rate is very high, right? When the cooling rate is very high. If the cooling rate is very high, the items they do not have the time and enough time to rearrange. As a result, so this guy will be very tough. Martensite, I'm sorry. Martensite is always brittle. What? Okay? Martensite is always brittle. Martensite, so this is martensitic is adjective. Martensite is a structure, it's usually brittle, hard. Brittle and hard. So the stress-induced martensitic transformation, that means, as you can see, stress-induced, if you press the stress, and this can result in this martensite. So this transformation is called martensitic transformation. That results in shear deformation and a volume change, because martensite has a different density, and martensite has a different density from its parent microstructure. As a result, when we have this martensitic transformation, the volume changes. The volume changes usually result in cracks. Because we know the mass does not change. The mass is conserved, right? in any reactions or this is a transformation, mass is conserved. Do you guys agree? If the mass is conserved, however, the density changes. The density of different phases, they are different. If there is a phase transformation, then definitely you will have volume change. The volume change usually results in the cracks. The ceramics dilatational strain. Dilatational strain, that means it is expansion. The ceramics that contain the second phase particle, the second phase, that is not the phase from this is the not from not particle is not from the parent material. A second phase particle that transform and often have incorporated the toughness, improve the toughness. And this one example, zirconium dioxide, and is the most widely studied material that exhibits a stress-induced martensitic transformation. So this is a material, the stress-induced martensitic, and here you can see. So this is a schematic and the stress-strain response of material that exhibits a martensitic transformation at a critical stress. Is a critical stress, and they have martensitic transformation. The strain changes, and then goes this way. So here is a particle, second phase particles that are around this crack tip. So here, this martensitic toughening mechanism transformation of particle near the crack tip resulting in a nonlinear elastic zone on the crack tip, the shielding. So here, so this is removed, right? Ki. And however, if we take a look in local, and we have Ki here for the case sigma c, and then we have these kind of things. You can see, so this one Ki and this Ki, and they are connected. So this is called the shielding. So this is a second mechanism, toughening mechanism. And then with third toughening mechanism is called the Dartle phase toughening. So ceramic, okay, ceramic, the Dartle material. So ceramics alloyed with Dartle particles and exhibit both bridging, and this is the process zone toughening. You can see, we have this is a crack tape in front of this crack tape in the neighborhood. We have these particles, so this is the process zone is a toughening. Right? However, sometimes here, guys, you can see sometimes the Dartle particles they are connecting, and this upper surface and lower surface. Actually, this is the bridging mechanism. So as a result, this is Dartle phase toughening, and sometimes the exhibit the combination of both process zone toughening and also this bridging toughening. So plastic deformation of the particles in the process zone contributes toughness, as does the Dartle rupture of the particles that intersect the crack plane. Right? So residual stress in the particles can also add to the material's toughness. The magnitude of the bridging and the process zone toughening depends on the volume fraction and the flow property of the particles. What is the flow property of the particles? That means if it is compressed on how this is the particle looks like, or how are they going to move this way or going to move this way? This is called flow properties. So the process zone toughening also depends on the particle size, right? Particle size with the small particles giving the highest toughness. So this is in addition, so this toughening mechanism is temperature dependent, and since the flow property of the metal particles vary with temperature, and we know that at high temperature, the Dartle material, Dartle particles, especially the metal particles, they become softer. Any questions regarding this process stone, and this is a process stone toughening. No question. And then we get this is the fiber and whisker toughening, right? As the name suggests, and we know that there are some fibers. You can see this figure, and so this is our crack. So we can see we have some fibers. Okay, these are fibers, and they are connecting the up surface of the crack and the lower surface of the crack. It means that if you want to make this is a crack propagate, and you need to break the bridging fibers. In order to break these bridging fibers, and you need to consume more energy. And as a result, this toughness of this composite will be increased. So you can see, this is what I just told you guys. One of the most interesting features of this composite is that combination of brittle ceramic matrix or brittle ceramic fibers or whiskers, resulting material with relatively high toughness. The secret to this high toughness lies in the bond between the matrix and the fiber or whiskers. Having a brittle interface leads to higher toughness than a strong interface. Thus, ceramic composites define intuition of a brittle matrix bonded to a brittle fiber by a brittle interface, resulting in a tough material. Right? So this is kind of intuitive content, but it is true. For this one, so this mechanism, this mechanism provides composite toughness well in excess to that predicted by the volume, by the rules of mixture. And you know the rules of mixture, right? Huh? If you mix the several different things together, the total mechanical properties of these mixed things, they depend upon the individual mechanical properties and the fraction of each of them. So you can see fiber matrix debonding, frictional threading along the interface, along with effect of bridging on the toughness. So you can see here a strain and stress. We go here then, and you need to have more energy. More energy. Stress is constant. You need to have more strain or more energy to break the bridging fibers or bridging whiskers and then go further. So you can see steady state cracking. So this is the fiber failure. See, at the very beginning it cracks, but you need to further crack all these fibers that are bridging these two parts. Then we talk about this the concrete and the rock. We know the concrete and the rock. They are in our daily life. We know this one very well. They are composites, and although concrete and rock are often considered brittle, and they are actually quasi-brittle material that are tougher than most of the so-called advanced ceramics. And in fact, much of the research on toughening mechanism in ceramic is aimed at trying to make ceramic composite behavior more like the concrete. We know concrete is very tough, right? In our driveway, or if we do some projects in our backyards, we need to have concrete the foundation. Have you guys ever helped your parents do something for some projects in the backyard and build a patio, this is the shed, and to build a shed you must have the concrete, the foundation, right? In order to mount all these pieces securely in the foundation, just in case there are very strong wind. And so this is you can see crack growth in concrete. This crack with two simplified models. Crack growth in concrete On process zone, we can see this is the particles idealized as a zone of string the softening. So this is on the process zone idealized by closure attractions. Process zone here, closure attractions. So this is a micro crack. The bridging is traction free of the crack. Okay, guys. So here, this Young's modulus. So this figure illustrates the typical tensile response of concrete. Of the small degree of nonlinearity caused by microcracking, the material reaches its tensile strength sigma t here, and then strength softening. And once sigma t is reached, the subsequent damage is concentrated in a local fracture zone. Virtually all of the displacement following the maximum stress is due to the damage zone. Note that the figure shows a schematic stress displacement curve rather than a stress strain curve. This is a displacement stress. And the latter is inappropriate because nominal strain measured over the entire specimen is a function of gauge length. So what I want you to know is the toughening mechanisms of what each of them, how each of them works. And also you can actually use your own language to tell me something about the concrete. Because concrete is a special brittle material that is commonly used in our daily life and in engineering applications. Right? Okay, guys, and so this is all I have today, and so I hope you have a wonderful Monday. I'm going to stop here. You're welcome.